transformers, diffusion models, GANs, retrieval augmented generation. The vocabulary of artificial intelligence updates almost daily. For researchers or domain experts applying AI, attempting to memorize this endless stream of model names is a fragile, frustrating strategy. Model names and technical architectures describe what a system is called, but they operate at a low, highly specific level. Because they change so frequently, they rarely help a designer or an educator identify what the tool can actually accomplish for a specific bottleneck. This spectrum illustrates how we currently categorize AI. At the bottom, we have those fast-changing model names. At the top are broad learning paradigms, like supervised or reinforcement learning. These concepts are stable, but they often sit too high to be actionable. Knowing a system uses unsupervised learning does not necessarily help you design a better medical trial. We are left with a gap in the middle. The AI Core Function Ontology fills that missing middle. Instead of categorizing by how the math works, this framework classifies AI by its functional capabilities. It acts as a stable bridge connecting architecture to intent. Harnessing this technology requires focusing on the specific functional capability AI performs in a given moment, aligning the tool with the actual problem. We can see this in a complex, real-world setting, like an AI-assisted drug discovery pipeline. When an autonomous lab develops a new chemical compound, it functions as a composition of specialized capabilities rather than a single monolithic model. Looking at this capability map, the process starts with the first logical prerequisite at the bottom, Function 1, represent. Before a computer can manipulate a raw chemical input, it must encode that physical molecule into a structured mathematical state, like a graph or an embedding. Once that representation exists, the data flows to Function 2, reason and infer. This function operates only encoded graphs to derive relationships. It looks at the molecule and infers toxicity risks, biological constraints, or potential binding affinity to a disease. Without encoding raw data and inferring constraints, no downstream action can occur. These first two functions form the non-negotiable substrate of the entire system. From there, the outputs from reason and infer feed the system's lateral engines. Following the path to the right, we reach Function 5, generate and create. The system takes those inferred biological constraints and uses them as specifications to synthesize entirely new candidate molecular designs. On the left is Function 4, simulate and emulate. We take those generated candidates and push them into virtual environments. This lets researchers forecast how a molecule will behave under physical conditions, bypassing the cost of synthesizing and testing failures in a real lab. In the center is Function 3, optimize and control. The system evaluates the simulated forecasts against its initial objectives, adjusting variables to optimize the molecule for safety and production cost. These lateral engines form a compositional loop. Generation creates candidates, which feeds simulation. Simulation yields performance data, which allows optimization. Optimization then dictates the rules for generating even better candidates on the next cycle. Overseeing the entire process is Function 6, autonomize and orchestrate. This function coordinates the individual tools, monitors the feedback loops, and manages the workflows of the fully autonomous lab. When decomposed this way, a system reveals itself as a deliberate capability graph, where distinct functional roles compose to break through complex scientific bottlenecks. Focusing on capabilities rather than code applies to diverse disciplines. Strip away the drug discovery data, and the architectural map remains intact. Applied to education, an AI tutor represents learner states, infers knowledge gaps, generates practice materials, and orchestrates feedback. In marketing, representing customer segments allows for inferring market needs and optimizing ad campaigns. In art, representing aesthetic styles allows for the orchestration of creative exploration. While the specific algorithms differ, the underlying functional roles, like representation, inference, and orchestration, remain the same across these very different fields. For learners and researchers, focusing on functional capability provides a clear path to grasp an AI system's utility without tracking every new software release. For designers and domain experts, this ontology provides a stable, shared vocabulary. It allows interdisciplinary teams to collaborate intentionally, building custom workflows based on what the AI actually contributes to the project. The next time you encounter a new AI model or a new platform, ask yourself, what core function is doing the main work here, and how does it depend on the functions around it? Model names will inevitably keep changing. A function-based map identifies the stable capabilities of AI, showing how those functions connect and how you can compose them for your own work.